Hey everyone, and welcome back to AI.Code.Cast. We're diving into a pretty cool coding problem today.
Yeah, a classic one. It's all about removing elements from an array, but here's the catch. We got to do it in place.
In place, so no cheating with extra memory, right?
Exactly. Think of it like this. You've got this array, this list of numbers,
Like it.
and you need to get rid of all instances of a specific value. Let's say for this example, we want to say goodbye to all the threes in an array.
So like if we have an array that looks like, let me see, like 3, 2, 2, 2, 3,
Perfect example.
and we want to get rid of all those threes,
Right.
what would we be left with?
You'd end up with 2, 2, and then it doesn't really matter what's left in those other spots.
Okay, got it. So it's like we're squishing those twos together and pushing the threes out of the picture.
Exactly. That's the essence of removing elements in place.
Right.
We're not creating a new array. We're working directly within the existing one.
Oh, so it's like we're decluttering and reorganizing without getting a whole new storage unit.
Exactly. We're all about maximizing efficiency here on AI.Code.Cast.
Love it. So this specific problem we're tackling today, it's called the Remove Element Challenge, right?
Yep, that's the one. And it really tests your ability to think about memory optimization.
So what are the rules of the game? What do we need to accomplish?
All right, so the problem gives us an array of integers, any bunch of numbers, and a target value that we need to remove.
Yeah.
Our task is to modify this array in place. So no extra memory, remember?
You got to do it within the original array.
Exactly. So that all the elements that are not equal to that target value, they're all grouped together nicely at the beginning of the array.
So in our example with the 3, 2, 2, 3, we wanted to get rid of the threes and have the twos at the beginning.
Exactly. The first part of the array should only have the elements we want to keep the non-target values.
Gotcha. And the function should return the number of these keeper elements.
Right on. In your example, it would return 2.
Makes sense.
Yeah.
But there's also this thing called a custom judge that adds another layer to this problem, right?
Ah, yes, the custom judge. Basically, it tells us that the order of the elements in the final array, it doesn't actually matter.
Really? So we have some freedom there.
Exactly, as long as all those keeper elements are grouped together at the beginning.
So the judge is only checking if the first k elements, where k is the count we return, are the correct non-target values.
You got it. It gives us a bit of flexibility in how we approach the solution.
Interesting. Now, before we dive into the really clever solutions, I have to ask, what's the most straightforward way to do this, even if it's not the most efficient?
Well, the most obvious way would be to create a brand new array.
Oh, okay. So like just start fresh.
Yep, and then you just copy over the elements that you want to keep.
So basically make a new list without the elements we're trying to remove.
That's the brute force approach. It gets the job done, but it's not exactly elegant or memory efficient.
Yeah, we're all about that optimization here.
Yeah.
And using a whole new array would defeat the purpose of doing this in place.
Precisely. Remember, on AI.Code.Cast, we're all about finding the most optimized solutions possible. And that means working within the constraints of that original array.
Right. No extra storage units allowed.
Yeah.
We got to work with what we've got.
Exactly. And that's where things get interesting because it forces us to think outside the box and come up with some clever strategies.
So how do we remove those elements without using any extra space? What are the secret tricks up our sleeves?
Well, there's a particularly elegant and efficient technique that we can use here. It's called the 2 pointers approach.
2 pointers. That sounds intriguing. Tell me more.
It's like having 2 assistants working in tandem within that array, each with a very specific role to play.
Okay, I'm picturing these little pointers running around in the array.
Haha, you got it.
What are they up to in there?
Let's give our pointers some names. We'll call them I and J. You can imagine I as this diligent organizer methodically placing the keeper elements right at the beginning of the array.
So I is like the curator making sure everything is in its rightful place.
Exactly. And then we have J, our scout, who races ahead, scanning through the array to find those keeper elements.
So Jay's is like the detective searching for clues.
That's a great way to put it.
So J is looking for the elements that don't match our target value, the ones we want to keep.
Precisely. And this is where the 2 pointers technique really shines. When J finds a keeper element, it signals to I saying, hey, I found a good one. Put it over here.
I love this teamwork. So it listens to J and dutifully copies that value over to its current position.
Yep. And then both pointers move forward in the array, continuing their synchronized dance.
Wow, so we're essentially compacting the array as we go overwriting those target values with the keeper elements.
That's it. It's like we're systematically pushing all the good stuff to the front of the line, squeezing out the unwanted elements.
This is amazing. So what happens if J encounters a target value? Does it cause a commotion?
Not at all. If J sees a target value, it simply moves on to the next element without bothering. I only moves when it receives a good element from J.
It's beautiful.
Hmm.
J is scouting, E is curating, and they're working together to achieve this in-place removal.
Exactly. And this process continues until J reaches the very end of the array.
Oh, so when J hits the finish line, what happens then?
Well, at that point, I will be pointing to the end of our newly compacted section, the boundary between the keeper elements and whatever's left over.
Ah, so E marks the spot where the good stuff ends.
Exactly. And the position of E tells us exactly how many keeper elements we have.
Brilliant. It's like using the array itself as a workspace to achieve this goal without any extra memory allocation.
You got it. And that's why this two-pointers approach is so efficient. We're not wasting any space.
I'm already loving this technique. But wait a minute, our source material mentioned that there are two-pointers approaches, right?
That's right. We've got another trick up our sleeve, and this one is particularly effective in scenarios where the target value appears very infrequently in the array.
Oh, so like if we only need to remove a handful of elements, this is the secret weapon?
You could say that. It's optimized for those situations where the removal task is more like removing a few grains of sand from a vast beach.
Okay, I'm intrigued. Tell me more about this sand removing technique.
Well, in this approach, we still have our two-pointers, but they take on slightly different roles. This time, we introduce a new pointer, we'll call him N, and he starts at the very end of the array.
So N is like a reverse pointer, marking the end of the valid portion of the array.
Exactly. Think of it as a boundary marker. As I moves forward, if it encounters the target value, we perform a strategic swap.
A swap. What are we swapping?
We swap the target value with the element at position N.
Oh, so we're sending those target values to the back of the line where they're out of the game?
Precisely. And after each swap, we decrement and moving our boundary marker one step closer to the beginning.
So the active portion of the array where we're still making changes is constantly shrinking as we go.
You're getting it. We're essentially squeezing those valid elements towards the front, pushing the target values to the back where they no longer matter.
This sounds incredibly efficient, especially when we don't care about the order of those discarded elements at the back.
Exactly. We're only concerned with that active section at the front where we're placing the keeper elements.
I'm loving these two-pointer strategies. They're so clever and efficient.
They both achieve those impressive results in terms of efficiency. Both have what we call O of n time complexity.
Meaning they only require a single pass through the array. Right.
Exactly. And since we're working in place, they both achieve O of 1 space complexity. No extra memory needed.
It's a win-win for efficiency. But now I'm curious, which of these two-pointers methods is the ultimate champion?
That's the million-dollar question, isn't it?
Is one inherently better than the other? Or are they both equally awesome in their own ways?
Well, that's a great question, and it leads us into a deeper comparison of these two approaches. The choice of which method to use really depends on the specific characteristics of the data you're working with.
So it's all about choosing the right tool for the job.
Exactly. Factors like the frequency of the target value within the array that will influence our decision.
Okay, I'm ready to dive into those nuances and explore the pros and cons of each approach in more detail. But first, let's give our listeners a moment to absorb all this two-pointers awesomeness.
Sounds good to me. We've covered a lot of ground already.
Two pointers, two approaches, and a whole lot of efficiency insights. Stay tuned, everyone, as we continue our deep dive into the world of in-place algorithms right after this.
Welcome back to AI.Code.Cast. Before the break, we were talking about those two clever two-pointer solutions for removing elements in place, both of which are super efficient, but each with their own little quirks and strengths.
Yeah, it's like we've got our classic copy method and then that optimized swap and shrink method, each using two pointers in slightly different ways.
Right, and they both dance through the array in a totally different way.
Yeah, I'm really eager to break these approaches down even further. Can we start with that classic copy method? I want to see how those pointers actually move through the array.
Absolutely. Let's revisit that first approach where we're carefully copying the keeper elements to the front of the array.
Okay, so it's all about the movement of our two pointers, I and J.
Hey, remember, I is our diligent organizer placing those keeper elements at the beginning, and J is the scout always searching for those keepers.
Right. And the magic happens when J finds an element that doesn't match our target value.
Right, it's like J is sending a signal to I saying, hey, buddy, I found one, put it over here.
Okay, let's actually walk through an example so we can really see this in action.
Yeah.
Let's say we have the array 1, 2, 3, 2, 4, and our mission is to remove all those 2s.
Perfect example. Initially, both I and J are pointing at the very first element, which is 1.
And since 1 is not our target value, we basically copy it onto itself. No change there.
Hmm.
Both I and j move to the next element, which is a 2.
And now things get interesting because 2 is our target value, so what does J do?
Well, j just skips ahead to the next element, which is a 3, while I is waiting patiently.
And 3 is a keeper. So J tells I, hey, copy this over to your current position, which is still at index 0.
Right, so we end up with 3, 2, 3, 2, 4.
Exactly. And both I and J move forward again.
J encounters another 2, so it keeps searching and lands on that 4.
Another keeper. What happens next?
Well, J tells I to copy that 4 over to its current position, which is now at index 1. So now the array looks like 3, 4, 3, 2, 4.
And now J has reached the end of the array, and I is sitting at index 2.
So that means the first 2 elements of our array now contain all the non-target values.
All those keepers all neatly grouped together at the beginning, just like we wanted.
We've effectively compacted all the desired elements to the front and pushed those 2's aside.
And our function would return 2, indicating the number of keeper elements.
I love how efficient this is.
Yeah.
We removed the target elements without needing any extra storage, just by rearranging what we already had.
It's all about making the most of the space we have.
Now let's talk about that other contender, the optimized swap and shrink method. You know, the one that's like surgically removing grains of sand from a beach.
Ah, yes. I love that analogy. This method is all about minimizing unnecessary steps.
Okay, so remind me how this one works again. We still have our 2 pointers, I and N, right?
That's right. It starts at the beginning as always, but this time it starts at the very end of the array.
Okay, so and is our boundary marker defining that active zone where we're still making changes?
Exactly. And as I moves along, if it hits our target value, we do a swap.
We swap the target value with whatever element is at position right. So those unwanted elements are kind of sent to the back.
You got it. And right after the swap and moves back one step, shrinking the active part of the array.
So the active section at the front gets smaller, while the discarded section at the back grows. It's like a 2-sided squeeze.
Exactly. Okay, so let's use that same example. 1, 2, 3, 2, 4. But this time with our swap and shrink method. Let's say we still want to get rid of all the 2's. Walk me through what happens.
All right, so I begins at index 0 pointing to that one, and starts at index 4 pointing at the 4.
Okay, so far so good.
It moves along and encounters a 2 at index 1 time for a swap.
Yep. What happens next?
We swap that 2 at index 1 with the 4 at index 4. So now we have 1, 4, 3, 2, 2.
And then
Moves back one step to index 3. That marks the new end of the active section. We're starting to see those discarded 2's pile up at the back.
what does I do next?
That keeps going and finds another 2, this time at index 3. So we swap it with the element at a current position, which happens to also be a 2.
So it's swapping a 2 with itself. It seems a bit redundant, but why is that step important?
Yeah. It does seem a bit redundant now that you mention it. But I guess it's important for keeping our logic consistent and making sure that it always marks the end of the active zone.
You're absolutely right. Even though it's swapping with itself, it ensures that our boundary is shrinking correctly. So what happens to and now?
It moves back to index 2. The active section is shrinking.
And that's a key point. Like, I will eventually reach n, and anything beyond n is considered discarded.
We end up with 1, 4, 3, 2, 2, and our function would return 3.
Exactly. It indicates the length of that valid section at the front.
This method is perfect for those cases where we only need to remove a few elements.
Just like removing a few grains of sand from a huge beach.
And just like our first 2 pointers method, it maintains that impressive O of n time complexity and O of 1 space complexity.
Yep, we're achieving amazing efficiency without needing any extra memory.
Both these 2 pointers methods are super clever and efficient. But I'm still thinking about which one reigns supreme. Is one truly better than the other?
It's not about one being better than the other. It really depends on the data we're working with.
So like if the target value is scattered throughout the array, our swap and shrink method is the way to go.
Absolutely. It avoids all that unnecessary copying and just streamlines the entire process. It's perfect for those sparse removals.
But what if the target value is more evenly spread out? Does the classic copy method make more sense in those cases?
You got it. If we see the target value more often, then those swaps in the second method might actually slow us down. The classic copy method, with its straightforward logic, might be a better fit in those situations.
So it's all about analyzing our data and choosing the most efficient method for that particular situation. It's like being a strategic coder.
Exactly. Understanding the subtleties each approach helps us write really optimized code. It's about knowing the techniques, but also knowing when to use them.
This has been such a fascinating discussion. I'm already thinking of all the ways I can apply these 2 pointers techniques in my own coding. But before we wrap things up, maybe we should give our listeners a quick recap of the key points.
Great idea. Let's distill all this two-pointers knowledge and give our listeners some food for thought. Stay tuned for the grand finale.
And welcome back to AI.Code.Cast. We've been exploring this really cool two-pointers technique for removing elements from an array in place.
It's pretty amazing how such a simple concept can lead to some serious efficiency gains, right?
Yeah, it's like we've unlocked these secret weapons in our coding arsenal.
Exactly. And the best part is we have two distinct approaches, each with its own strengths depending on the situation.
Right, so it's not a one-size-fits-all kind of thing. We need to choose the right tool for the job.
Absolutely. Let's quickly recap those two approaches just to make sure everyone's on the same page.
Okay, sounds good.
We started with that classic copy method where our pointer J scouts ahead looking for those keeper elements.
Right, and then it signals to pointer I to copy those elements over to the front of the array, nice and organized.
Yep, and that method really shines when that target value is kind of spread out evenly throughout the array.
Yeah, it's super straightforward and always efficient.
Then we moved on to the optimized swap and shrink method, where pointer N is like our boundary guard.
Right, we're swapping those target values to the back and shrinking the active section as we go.
Exactly. And this approach is perfect when the target value is like a needle in a haystack appearing only a few times.
Both of these methods achieve that impressive O of n time complexity, meaning we only need to go through the array once.
And because we're working in place no extra memory, they both have that O of 1 space complexity.
It's a win-win for efficiency. We're saving both time and space.
Now, the key takeaway here is that there's no single best method. It all comes down to understanding our data and choosing the right approach for that specific situation.
If we have a target value that's all over the place, the swap and shrink method is the clear winner. But if it's more evenly distributed, the classic copy method might be a better fit.
It's like we're code detectives analyzing the clues and choosing the best strategy to crack the case.
I love that analogy. It's not just about knowing the techniques, it's about knowing when to use them.
Coding is all about problem solving and finding those elegant and efficient solutions.
This deep dive into the two-pointers technique has definitely equipped our listeners with some valuable tools for their coding journey.
And hopefully it sparked some new ideas and inspired them to explore even more clever algorithms out there.
That's what we love to see. So until next time on AI.Code.Cast, keep those coding brains engaged, and remember the most efficient solutions are often the most elegant ones here.